Hello everyone, welcome to our CHI-230 session. This is coordination chemistry and our today's topic is how to calculate microstate table for NF1 configuration. Okay, for NF1 configuration there is F1 means 1 electron in F shell. So before that we have to calculate number of microstates. So here it is formula to calculate number of microstates, that is capital N factorial divided by small n factorial into bracket capital N minus small n factorial. So this capital N is equal to total electron which are present in F orbital, or the capacity of F orbital to carry the electron. So the capacity of that F orbital is 14 electrons. That's why capital N is equal to 14. Then small n is equal to how many electrons are present in that configuration. There are only one electron because system is NF1 or the configuration is NF1. So small n is equal to 1 electron is there. That's why small n is equal to 1. So 14 factorial divided by 1 factorial into bracket 14 minus 1 is equal to 14 into 13 divided by 13 is equal to divided by 1 is equal to 14. Okay. So total number of microstates which are present in NF1 configurations are 14. Now how to calculate ML and MS value. ML means orbital number or orbital quantum number and MS means total spin quantum number. Okay. So how to calculate ML? ML is equal to summation I, ML I is equal to, there are only one electron, that's why ML1, okay, and ML1 is equal to 3 because here it is F orbital, okay. So F orbitals having subshells 1, 2, 3, 4, 5, 6, 7 and the number of orbitals or subshells are 0, minus 1, minus 2, minus 3, plus 1, plus 2 and plus 3. So in first shell, that is plus 3 shell, maximum ML value in NF1 configuration is 3. This is orbital number, plus 3 is orbital number. So maximum ML value is plus 3. If only one electron is there, then we can put that electron in this first shell and the probability or maximum ML value we can calculate from this configuration is 3. Okay, if we put one electron in this shell, then ML is equal to 3. If we put one electron in this one shell, second shell, then ML is plus 2. But maximum ML possible in this configuration or in this orbital is plus 3. That's why ML is equal to plus 3. So what is range of ML? That is plus 3 to plus 2, plus 1, 0, minus 1, minus 2 and minus 3. This is range of ML. And what about MS? There is only one electron in that configuration. That's why MS, and that electron gives positive spin. If we put that electron like this, if we draw that orbital, if this one is F orbital 1, 2, 3, 4, 5, 6, 7, if this one is F orbital and this one is 0 shell, minus 1, minus 2 and minus 3 shell, then plus 1, plus 2 and plus 3 shell. If we put one electron, so ML is equal to plus 3. Okay, so ML is equal to plus 3. That ML is a orbital number. So for that one electron, NF1 configuration, ML is equal to plus 3. And what about MS? MS is a spin number. Okay, so this electron is this electron shows positive spin. It is plus 1 by 2. Spin of that electron is plus 1 by 2. That's why MS is equal to plus 1 by 2. So range is either it is plus 1 by 2 or minus 1 by 2. So range for MS is equal to plus 1 by 2 to minus 1 by 2. Now our next task is to draw the microstate table. Here in this case, here it is a microstate table. Okay, for F1 configuration. Now for this microstate, we can draw microstate table and we can fill MS value in horizontal row and ML values in vertical column. Okay, so MS value or the range of MS values are plus 1 to minus 1 by 2. MS is equal to plus 1 by half spin or minus 1 by 2 spin. And what about ML? ML value or range of ML value is equal to plus 3, plus 2, plus 1, 0, minus 1, minus 2 and minus 3. Okay, so write down from +3 2 1 0 -1 -2 and -3. This is range of ml, and ms is equal to +1 and +1 by 2 and -1 by 2. Now there is only one electron. Okay, so in this case here it is orbital, f orbital. So we can put one electron, then we one electron in that fashion. After that we get +3 ml or +1 by 2 ms value. If we put that one electron in first shell, or that electron is having positive spin, or that electron is positive, then the ml is +3 but ms is +1 by 2. Then ml is +3 and ms is +1 by 2. So electron is in +3 state, +3 shell. Okay, so write down shell number, that's why it is 3. And what is this plus or plus sign indicates? This sign indicates spin of electron. If spin of electron is positive, then this sign indicates, this sign is positive. And if spin of electron is negative like this, then this sign must be negative. But in this case we put that electron in first shell. Okay, we put that electron in first shell and that electron gives positive spin. That's why ml is equal to 3 and ms of that electron is positive, that is ms, that is spin of that electron, that is +1 by 2. So this one is a this sign is for only for spin. Okay, now in this case ml must be 3 and ms is -1 by 2. Now put that same electron in that same subshell, but spin is, the electron must be inverted position. That's why that electron will give negative spin. Okay, so now ml of that electron is +3. Okay, this +3 matches with that electron, and ms is equal to -1 by 2. The spin must be negative, or that electron spin indicated by this negative sign. Okay, then next case, ml is 2 and ms must be 1 by 2. Now we have to put that electron in that particular shell, then we will get ml is equal to 2 and ms is equal to 1 by 2. Now put that electron, we have only one single electron, so now put that electron in this shell. Okay, forget about this electron, we put that electron in this shell. Okay, now ml of that electron is +2. So ml is +2 and ms is 1 by 2. Okay, so electron is in +2 shell, so write down 2 because this is shell number. And what about that sign? Electron gives positive sign, so put that positive mark or positive sign above this 2. Okay, so this is microstate of this second electron. Now in this case ml is 2 and ms is -1 by 2. Now put that electron into inverted position, then you will get ml is shell number, orbital number, that is +2. Okay, and ms is -1 by 2. So it is ml is -1 by 2. So write down that 2, but the spin is negative at the top of that 2. Okay, then what about this case? ml must be 1 and ms must be 1 by 2. Now put that same electron, single electron, put this electron into this one in parallel positive spin. So the ml is equal to 1 and ms is equal to -1 by 2, sorry +1 by 2. Okay, then for this case put that electron inverted position, in inverted position. Okay, then you will get ml is equal to, that is +1 and ms is equal to -1 by 2. The spin of that electron is -1 by 2. So -1 by 2 and ml is equal to 1. Okay, now next case, put that electron in this suborbital, then you will get ml value is 0 because the shell is 0 for that electron, and the spin of that electron, that is spin value, is +1 by 2. But when we put that electron in inverted position, then ml value is 0 but ms value is -1 by 2. Okay, like this we have to draw the microstate table for NF1 configuration. This is very simple to draw the microstate. Now our next task is to assign terms for that microstates. Okay, so here it is 2F, doublet F, these are terms. So what is meaning of the terms? So and how to assign the terms? For this doublet F, we have to check this is Russell sounder term or ground state term. This is ground state term. So for ground state term, there is a formula. We already have discussed the formula for ground state term, that is 2s plus 1 L. This is formula for ground state, and if it is spectroscopic term, then J is also there. J is a special quantum number. That quantum number is spin orbital type of coupling, or that quantum number means the spin orbital coupling. Okay, so for term symbols or ground state term, we only require that 2s plus 1 and L. This is ground state term. Okay, so 2s plus 1 is a spin multiplicity, and that L is equal to orbital type of coupling. So in this case, the spin multiplicity of this microstate, we have to calculate the spin multiplicity. So here it is spin is plus 1 by 2. Now if spin is plus 1 by 2, then 2s plus 1 is equal to, if put that value of s into this 2s plus 1, then 2 into 1 by 2 plus 1, then spin multiplicity is 2. Now this one is a 2 is a spin multiplicity, or that is doublet. And what about term? We already discussed about terms. That is, there are different terms S, P, D, F, G and H. These are terms, and these are ml values 1, 2, 3, 4 and 5. 0, 1, 2, 3. If ml is equal to 3, then term must be F. Okay, ml is equal to 3, then term must be F. So just write down term symbols, that is 2s plus 1 L. 2s plus 1 is doublet, and L value for F is equal to, L value for 3 is equal to F term. Okay, so it is doublet F. By using this 2s plus 1 L and J, by using this formula, we can calculate terms or ground state term. Okay, so write down term, then put that term from top to bottom in this same line, and put that term from left to right in the same line. Okay, then you will get doublet F, doublet F, doublet F, doublet F, doublet F, doublet F and doublet F. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 times you will get doublet F. Now we have to calculate what is degeneracy of the terms. Okay, so here it is, next point is for degeneracy. How to calculate total multiplicity or degeneracy. So formula for that, there is a formula to calculate degeneracy, that is 2L plus 1 into 2S plus 1. For that doublet F term, we have calculated this term, that is doublet F, by using 2S plus 1 L and J formula or term symbol. Okay, so for that 2F or doublet F, the total multiplicity or degeneracy we can calculate by this formula, using this formula. That formula is 2L plus 1 into 2S plus 1. Now put that value of L. So L is equal to, in this case L is equal to 3. So 2 into 3 plus 1 and 2S plus 1, that is spin multiplicity. So that spin multiplicity is 2. Okay, this 2. So put that value into this formula, that is 2 into 3 plus 1 into 2 is equal to 14. So total multiplicity or degeneracy is 14. So now let us check is that 14 is correct or not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so this 14, we get that degeneracy or multiplicity of degeneracy 14 is correct, and this 14 number is matches with our this table or the degeneracy or term symbols from that microstate table. Okay, now our next point is to calculate J values. So what is J values? J value means there is a coupling, that is a special type of coupling. That coupling is spin orbital type of coupling. Okay, or J values. J values for doublet F. Now we will get that we get that term from this microstate table. We already have calculated that term is doublet f, and for that doublet f we are going to calculate J value. So that J value is either L plus S or L minus S. When orbital is less than half filled, the J value is L minus S, but when orbital is more than half filled, then J value or that spin orbital coupling is L plus S. Now for doublet F, L plus S for doublet F, L is equal to 3 and S is equal to 1 by 2. That's why 3 plus 1 by 2, 2, L minus S, 3 minus 1 by 2. Then 7 by 2 to 5 by 2. 3 plus 1 by 2 is 7 by 2 and 3 minus 1 by 2 is 5 by 2. So J values are from 7 by 2 to 5 by 2. Okay. Now our last point in this problem to describe the splitting pattern of NF1 configuration. So what is splitting pattern? If that configuration is NF1, one electron in F orbital, then NF1 orbital splits into two different energy levels. First one is a degeneracy of that first energy level is doublet F. Okay, so it is Russell Sounder term or total spectroscopic symbol, that is doublet F. This is spin-spin multiplicity, this is orbital type of coupling, and this is spin orbital type of coupling or J. So that J is from 7 by 2 to 5 by 2. So doublet F, in this case doublet F 7 by 2 to doublet F 5 by 2. Okay. So this is last one point, that is a splitting point. So here in this problem NF1 configuration, in NF1 configuration, first we have to calculate number of microstate by using this n factorial formula. Then our next task is to calculate ML value or the range of that ML value, then MS value, then draw the microstate table, then calculate the total multiplicity or degeneracy. Okay, for this by using this formula, then J value, that is special quantum number, spin orbital quantum number, and last one is a splitting pattern of that particular configuration or NF1 configuration. Okay, thank you.